Luigi launches a boat from point A on the bank of a uniform straight river that is 4 kilometres wide. He wants to reach the point B, which is located 10 kilometres downstream on the opposite side of the river, as quickly as possible. He could row his boat directly across the river to a point C, as shown in the diagram, then run all the way to B, or he could row directly to B. He could also row to some point D, which is between C and B, and then run the remaining distance to B. We know that Luigi is able to row at a speed of 6 kilometres an hour and run at a speed of 8 kilometres an hour. Part A asks us to give an expression for the time t that it takes Luigi to travel from point A to point B in terms of x, where x can vary as the position where he lands between C and B. So the first thing we need to do is work out what the length of AD is. So hopefully you'll agree that this here forms a right angle, which means we can use Pythagoras' theorem to work out what the distance of AD is. So AD squared is going to be equal to AC squared plus CD squared. So that's just Pythagoras' theorem. So if we calculate AD, that's going to be the square root. We're going to take the positive because it's a length. And AC squared is 4 squared, which gives 16. And then CD is the length x, so that squared is just plus x squared. Then we can also work out what the distance is between D and B. And the distance dB is just equal to 10 kilometres subtract x, or the remaining distance that he has to run from the point he lands at D. So the next part we need to do is work out what the time will be. So we know that time is equal to the distance over speed. So that means that we can write our function t in terms of x as the distance of AD, which is 16 plus x squared, divided by the speed at which he can row the boat, because A to D is crossing the river in his boat, and that speed is 6 kilometres an hour up here. So we divide off by 6, and that gives the time of the journey that he is rowing. And then we add on to that the distance of dB, which is 10 minus x, and we divide that by the speed at which he's running. So when he runs at 8 kilometres an hour. So that there is the function which describes the time taken in hours, depending on where Luigi lands his boat at the position x. For part B, we want to find the position x where Luigi should land to minimise the time taken to travel from the point A to the point B. So we know that to find the minimum, we look for a stationary point on a curve. So we're going to set the derivative t dashed of x equal to 0, and we can use our calculator to quickly solve this. On the CAS calculator, go into the main menu. The first thing we want to do is define our function t, which describes the time it takes with respect to x for his journey. So we found previously that the time was equal to the square root of 16 plus x squared, all divided by 6. And then we add on the running journey, which is 10 subtract x over 8. So if we highlight that, interactive define, we can define that using the ABC as being capital T of x, the time. Then we can use our calculator and calculate the derivative by going interactive calculation diff. And we want to then set this equal to 0 to find any stationary points that are on the curve. So interactive equation inequality solve for x, and we get that x is equal to 12 root 7 divided by 7, which will give us a stationary point. So the calculator says that the value of x, which gives a stationary point, is 12 root 7 divided by 7 kilometres from the point C. Using this, we want to state the amount of time it takes in hours such that the journey is completed in a minimum amount of time. And we want to state our answer correct to 2 decimal places. So to do that, we're going to substitute in the value of x we found in part B, which was 12 root 7 over 7. So to do this, we're going to use our function as we had before, which is t, and we're going to substitute in this 12 root 7 on 7. If we hit execute, that is the time that it takes, but we want that correct to 2 decimal places. We find that the time taken correct to 2 decimal places is 1.69 hours. We can also check that this is a minimum using the graphing feature of our CAS calculator. On the calculator, we can show that this is a minimum using the graphing feature. So if we click on the graph icon, and now what we want to do is get our t of x, which was all the way back up here, and drag it into this screen. And we can see there's a bit of a minimum going on. We can resize this to go between 0 and 15 hours, and then we can go from a time of 0 to say a time of around 3, because we knew the minimum was about 1.69, so we'll just go a little bit higher than that. And now if we go analysis gsolve minimum, we find the minimum point is at 4.54, which is the same as 12 root 7 on 7 if we approximate it. And the time there is 1.69 hours, which is the same as what we found previously. Therefore, our calculator confirms that landing approximately 4.54 kilometres on the opposite side of the bank will give a minimum time for his journey, which is 1.69 hours correct to 2 decimal places.